Good morning. Today we're going to do section 5.5. Three sections left: 5.5, 5.6, 5.7. We're going to cover them this week, and then next week we'll do a couple of days of review, and then you'll have your last assessment on Friday, June 5th, I think it is. All right. Yeah, it is Friday. Just checked. It's Friday, June 5th. And that would be a quiz on all of Chapter 5, and that is it. All right. And then we will spend the week of the 8th through the 12th just making up any work. Anybody needs to make up anything, probably just meet one more time over Zoom to say goodbye to you guys. And then we'll be done. So by June 5th, we will be done pretty much everything. Okay. So real short lesson today. All right, so talking about bases other than e. So we recently just talked about having the derivative of and integrating e to the u, right? Well, what happens if the base is an e? Now, we've already, this first example, where you have a variable raised to a constant. Well, x to the fifth, 2x minus 7 cubed. We've done these before, right? This is just your basic, bring your 5 out. The derivative of this is 5, x to the fourth. Here you do the chain rule, right? We've done this since the beginning of the year, all right? Integrating it, u to the n, we've done this. You add 1 to the exponent, you put it over the exponent, all right? So nothing new here, all right? Now, we have the opposite here for the second thing that can happen. We have a constant to a variable, all right? This is what we just did before, where we had e to the 5x, right? E to the 5x. And we had e to the u du. So like the derivative of e to the 5x would have been e to the 5x times 5, where you rewrite the original times the derivative of the exponent. Okay. Now, what happens if that base is not e? What if we have something like we have here, where it is 3? All right. So we have 3 to the x, or we have 5 to the tangent x, where we have a constant in the base and the exponent has the variable, all right? A constant to a variable. Well, if it's e, then it's e to the u du. But if it's anything besides e, then we have this new formula, which where you can find that, correct, on your formula sheet, all right? So when they say a, it's a is any constant, all right? A is any constant. And let me just take a second and zoom in. I'll miss this stuff, but that's okay. All right, so right here. Okay, all right, so new formula, all right? So it's a to the u natural log of a du, all right? So it's just like you're following a recipe when you have a situation like this. You have 3 things you have to do. You have a to the u, which means you're going to rewrite it. You're then going to write the natural log of a, which is the base. Then the du is the derivative of the exponent. So you're going to rewrite natural log of the base, the derivative of the exponent. Like I said, you don't have to memorize this, so you just have to go through it. So for example, find the derivative. Y equals 2 to the x. We have a constant raised to a variable power. So we're going to use this formula right here. So a to the u means we rewrite this. So it's 2 to the x times the natural log of a. In this case, a is 2, right? It's the base, times the derivative of the exponent, which is 1. So it's just 2x, 2 to the x, natural log of 2. That is your derivative, all right? This right here, because times 1. That's all you have to do, all right? 5 to the sine x, same thing. A to the u means just rewrite 5 sine x. Oops. That needs to be in the exponent. Doesn't look like it when I write it like that. Sorry. 5 to the sine x times the natural log of a, which is just 5, times the derivative of the derivative of sine is cosine. If you forget that, guess where that is? Also in the formula sheet. Now, just leave it like this. You don't have to do anything else. There's your derivative. Don't try to make it look all fancy. Just write it like that and circle it. You're done. Okay? 3 to the 5x. Same thing. We have a constant that's not e. All right? So we follow this formula again. You rewrite it times the natural log of the base, which is 3, times the derivative of the exponent, which is 5. There's your answer. All right. The last one here. All right. Oh, it's e. So we go back to this formula. So it's e to the u du. So you do it. All right. Times, what's the derivative of the exponent? Well, it's negative, right? 4 cosecant 2x cotangent 2x times 2. Now, yes, could you make this -8? You could. I don't care if you just leave it like that. It's fine. All right. Remember, where did this cotangent come from? Because the derivative of cosecant is negative cosecant cotangent. We kept the inside the same. We multiply by the derivative of the inside, right? So -8 cosecant 2x cotangent 2x times e to the 4 cosecant 2x. That's the best way to write it. All right. Now, if you realize these formulas, even though they look different, are basically the same. All right. Even if you use this formula for an e, the only thing that's different is this part right here. Well, if you have e, what's the natural log of e? It's just 1, which is this formula. So these basically are the same. All right. But it's just easier if we just look at them separately. All right. But they would give you actually the same answer. Even if you use this formula a to the u for an e to the u, you get the same thing. All right. So now let's do the opposite. Let's do the integration. Remember, we just did this, where if you have e to the u du, it's just e to the u plus c. Well, if you have a to the u du, which means you're going to have any other constant to the u, it's going to be this, a to the u over natural log of a plus c. Okay, so what we're going to do is this just, if not only if you have e raised to an exponent, if you have any other constant raised to it, we are going to use the exponent as our u. So this is a practice of what we had done previous. U is just going to be x squared. The derivative of x squared is 2x dx. I'm going to put a 2 here, right? So 2 there, there's my du, so I put a 1/2 on the outside, e to u du, which is 1/2, and then you have e to u du, which is e to u plus c, so it's just e to the x squared plus c. There we go. All right. Now, here we have sine x times 2 to the cosine x. We have a constant that's not e, all right? But we're still going to make u the exponent. So I make u cosine x. The derivative of cosine is negative sine x dx. So I have sine x, I have dx. I'm just missing a negative. So negative 2 to the u du. Everything that's underlined here is just my du. So now I have some constant, any constant that's not e, raised to the u du. So I use this. So now just write what it says. So it's negative a, which is in this case is 2, to the u, which is cosine x, over the natural log of a, which in this case is 2, plus c. There we go. All right. The reason this is negative because the derivative of cosine is negative sine. We need to add that negative in there. All right. This one looks complicated. Let's say 4 minus x, that whole thing squared, 3 to the 4x. Now you might be like, oh, I can make it 4 minus x, but this, you see a constant like this being raised to some exponent, there's a variable in it. Let's make u the exponent. If you tried it as 4 minus x squared, you would quickly realize you're wrong. All right, 4 minus x cubed. All right, what's the derivative? We have to use chain rule. All right, 3 comes outside, 4 minus x squared, and the derivative of the inside is negative 1, so I'll just put a negative there. So I have 4 minus x squared. I have a dx. I need to add a -3 there. So we'll put a -1/3. All right, 3 to the 4 minus x, which is my u, and everything that's circled here in the purple, all right, is my du. So I end up with -1/3 integral of 3 to the u du, which is just -1/3 a to the u, which is times 3 to the 4 minus x cubed over the natural log of a, which is 3, plus c. And there's your answer. These threes don't cancel. Don't cancel. All right. So it's exactly what we were doing before. It's just a new way of making a u. If it's x is in the exponent, it's not just e raised to a power, but you also have another constant raised to a power. Okay. And then the last type of example, which I'm actually just going to go through and, I'm just going to do one of these because we're really not going to have many examples of this, but I want to show you this, is if you have a variable to a variable. So you have a variable in the base and a variable in the exponent. The only way we can do this is we can't do the integral, we're going to do the derivative, is use logarithmic differentiation. So for example, you take the log of both sides. So natural log of y equals the natural log of x to the x. Okay. So you would have to end up doing is bring the x out to the front, right? So natural log of y equals x times the natural log of x, and take the derivative of both of these. Okay, so for example, this just turns into 1 over y dy dx, and that's what we're going to end up solving. And this, you would have to do the product rule. Well, so it's the first times the derivative of the second. Well, what's the derivative of the natural log of x? Well, the derivative of a natural log is du over u. So this would be the derivative of the inside, which is 1 over x times the whole thing, all over the whole thing, sorry. And to be honest with you, I don't know why I picked this one, because this one's going to be worse than the first one, okay? Plus the second function, which is the natural log of x, times 1, because the derivative of x is just 1, all right? Then what ends up happening is you take all of this and multiply it by y, which is just this guy, all right? Now, we would not want to leave this like that, all right? Remember, the reason this was because it's d over u, which is f, all right? Now, just to show you this one real quick, which I've probably just done the first time. Like I said, we're not really going to have to worry about this, but I just wanted to show you in case you ever see this again in another course. Natural log of x sine x. This is one's much nicer. So it's natural log of y equals sine x natural log x. Yeah, no one likes this one. All right, this one's much more basic. All right, same idea, 1 over y dy over dx equals, now the derivative, so there's a product rule again. So it's the first, which is sine x, times the derivative of the second, the derivative of natural log of x is 1 over x, plus the second, which is natural log of x, times the derivative of the first, the derivative of sine x is cosine x. All right. And I don't care, normally you don't want this here, but that's fine. It'd be sine x over x. Put that in parentheses and multiply by y, which is this, x sine x. And there is your answer. That would be your derivative. All right, so that's the idea. You just use logarithmic differentiation, variable to variable. Like I said, we're not really going to have that. Don't have to worry about that too much, all right, or if at all for us for right now. All right, I'm going to concentrate more on obviously e to the u and a to the u types of problems. And then obviously what we did up here. We've done this forever. Okay. All right, so that's it for 5.5, and hope you guys have a good day.